Hello, welcome to Financial Math for Actuarial Exam 2 video number 172. In this video we're doing a generalization of the October 2000 SOA Sample Exam problem number 127. We did the actual problem 127 in the last video, video number 171. I'll put a link to it up here in the upper right corner. You're definitely going to want to watch that video before watching this one. This one, by being a generalization, is definitely more difficult. You're going to need to really concentrate to get as much out of this video as you can. Also might be helpful to see some related posts on my blog, infinityisreallybig.com. Immunization Part 3 is about video 171. It's already on my blog. Immunization Part 4 is a post I will make after posting this video on YouTube in the next day or two, here in February of 2019. All right, so here is the problem statement. Again, this is pretty similar to the one in video 171, just more general. A company owes $500 and $1,000, some liabilities, to be paid at the end of year 1 and year 4 respectively. The company will set up an investment program of assets to try to pay for those liabilities. To do it, it sets up these assets with two conditions. We want to match durations and present values of the above obligation, the liability cash flow, using a certain interest rate, I0. Okay, that's an arbitrary interest rate in this video. That's something new. The investment program produces an asset cash flow of capital X today at time 0 in the present, and capital Y in little y years. Okay, so little y is arbitrary now. In video 171, the last video, I0 was 10%, 0.10, and little y was 3. Right? And we saw that this was not enough to immunize the liabilities by the assets. So that was kind of thought of as being a bad thing. And the big picture of this video is, can we fix that? And how do you know whether you can fix it or not? So we're using this computer program, Mathematica, that you see here to help us. Part A, we want to calculate capital X and capital Y, these payments, at time 0 and at time little y, not as numbers, but as things that depend on I0 and little y, really functions of I0 and little y. Since they're functions, they can be graphs. So we'll use Mathematica to make graphs and discuss what we see. Try to note any interesting things. Then part B. Again, in that last video, immunization, neither full nor Redington could be achieved. But maybe if little y, for example, is bigger, maybe we can achieve Redington immunization, for example. We'll try to see if we can do that. We'll make graphs and discuss what we see. Okay? So get ready here. This is challenging, but I think worthwhile. I think this really illustrates some cool things for one thing and helps you think more broadly about what's really going on with these things. Not just focused on problem solving, but also understanding. This Mathematica code that we see here is going to make a time diagram for us, but it's not a static time diagram. It's something I can change. Okay, manipulate is what does that for me. So it's a time diagram. We see the asset payments of amount capital X at time 0 and amount capital Y at time little y. And I can change little y, and that also changes where capital Y is as well. Okay, and as little y changes, the values of capital X and capital Y can change as well. Capital X and capital Y will depend on little y as well as I0. You've got the liabilities of 500 at time 1 and 1,000 at time 4. Okay, this diagram then helps you set up your present value functions. PA of I is the present value of the assets at an arbitrary interest rate I, and PL of I is the present value of the liabilities at an arbitrary interest rate I. We're discounting these things back to time 0, and you can get these equations. If you're watching this video, this should not be difficult for you, okay, if you've gone this far. Matching these things at I equals I0 will be matching present values. We also know to match durations that we want to take the derivatives of these things with respect to I and set those things equal to each other at I equals I0 as well. By the way, here V is the usual V. It's 1 plus I all to the negative 1 power. All right, let's now get into the algebra. Matching the present values gives us this equation. So that's one of the two equations that we need to solve for capital X and capital Y. Again, not as numerical values, but as functions of I0 and little y. In solving these things, you want to think of I0 and little y as fixed. Matching durations means matching present values and matching these derivatives. So we get this equation here. Okay, you should double check these things. One thing that happens here is some negative signs get canceled to get this. This system of two equations in pink here and two unknowns, capital X and capital Y, is not too hard to solve by hand. We can substitute the second equation into the first. In other words, replace this expression here with this expression here and solve for X and get this. Okay, you should take the time to double check that either by hand on paper or in your mind. Then we can take that expression, plug it back in here for X and solve for capital Y, and you'll get this. Okay, so these are the part of the answer to part A. These are our two functions, capital X and capital Y, as functions of little I0 and little y. Let's have Mathematica check that. Solve can be used to solve equations. Here's the first equation. The double equal sign, by the way, is just a way of indicating to Mathematica that we want to solve an equation. And here's the second equation right here. And this is saying we want to solve for X and Y. It gives answers that are kind of complicated looking, and they don't look the same as these answers here and here, but looks can be deceiving. If I take my answers in pink that I found by hand and apply the together function to them to combine the fractions into one fraction with a common denominator, this one and this one individually, I see that I get the same expressions. This matches this, that's what X is, and this matches this, that's what capital Y is. Okay? So now I'm going to use the simpler expressions to define these as functions of little I0 and little y. That's just Mathematica's syntax for doing so here. These are functions really of two variables, I0 and little y. If we're going to make a true graph of such a function, ideally you make a graph in 3 dimensions. These are going to be surfaces, two-dimensional surfaces in 3 dimensions, and that's what plot 3D does. And you can certainly make this plot that you see here. It's not super enlightening unless you think really carefully and rotate it a bit as you think about it. It is a graph of three functions here. The pinkish one, or red over here, is the value of capital X, the monetary amount paid at time 0. And this labeling is not ideal. We really have I0 in here as part of our dependence as well. Hope you don't mind me changing this midstream. That makes this kind of messy over here. I0 is going left and right, increases to the right. Y is going into the screen, increases into the screen. The output is up and down. Pink graph is the value of X, that's the payment at time 0. It's a little hard to see, but there's a bluish graph in there, that's the value of capital Y. And there's a green graph in there, that's the value of the difference, capital Y minus capital X. Okay, this is difficult to look at. It's easier to instead make ordinary graphs, for example, like this, showing these things as functions of one variable when the other variable is fixed. Okay, and essentially these are what are called slices or sections of the three-dimensional graph, the surface in 3 dimensions. So what do we have here? We see I0 is 0.1. That's the same as the value, 10% from video 171. We see functions of little y here, functions of the time of payment of capital Y. You got to keep these financial things in mind. What was the situation? Always keep this picture here in your mind, right? Draw it here. Pause the video and draw it if you need to, okay? Because it's going to be important here as you continue to think about what the real life situation is here. What is this showing us? This is showing us a number of things. For one thing, it's showing us that the value of capital X increases as little y increases. The payment amount at time 0 has to be higher if the other payment amount at time little y is further in the future to match present values and durations. And the value of the blue graph, capital Y, goes down. Okay, so as little y, the time of the second payment for the asset cash flow is larger, the payment amount at time 0 gets larger, and the payment amount at time little y gets smaller. The green graph just helps you see what the difference is. Capital Y is how much bigger than capital X, and the difference goes to 0 is pretty obvious from the picture. You might wonder, does the difference become negative? Does the red graph cross the blue graph? You might wonder that. That's a question you could try to answer. In fact, we also see an interesting thing, that the red graph is 0 at some point, maybe around little y equals 2.8. I can use solve to solve for those things. Yeah, about 2.8 is the value of little y where capital X becomes 0. So if the second payment is at time approximately 2.8, you want capital X to be 0. Okay, no payment at time 0. Is there a negative payment if little y is less than 2.8? That's what this is saying. Okay, now that doesn't really make sense as far as assets go. So what that's telling you is, as far as real life thinking about asset cash flows, you would definitely want little y to be bigger than 2.8. Okay, and you might also wonder again, do these graphs cross? Does capital X ever equal capital Y? And it looks like they do. I could try to graph it out further to see if that really is the case. 2.22 or 10.22 is where they cross, and evidently when y is bigger than that, then the red graph is higher than the blue graph. The payment at time 0 is higher than the payment at time little y. I could turn this around, and by the way, I can also change I0 here to look at different slices. High interest rates make the difference between these two graphs maybe not go to 0. That's interesting. I mean, maybe they cross still, but it's hard to tell. Low interest rates, the graphs cross earlier. Okay. For smaller values of little y, the red graph will be higher than the blue graph. All interesting things to think about. We're thinking about things conceptually and finding out things you would never guess by just looking at the problem statement when we make these graphs. And it also solves infinitely many problems at once. We could use these graphs to estimate values. And we could also, because we have Mathematica here, we could plug numbers in. Okay. For example, the answer from the last video for x when I0 was 0.1 and y was 3 was about 75, I think. Yeah, 75.36. That was one of the answers from the last video. We could also think about the graph differently. We could slice it to get functions of I0 for different values of little y. So here little y is 3. Here I've got the red and blue graphs as functions of the interest rate, I0. Okay, not as dramatic of changes in these graphs as I0 changes. And we might also, well, okay, if y is small, the graphs diverge quite a lot. And if y is big, they diverge quite a lot. They're more radical in their behavior when y is either small or large. And once again, we see that when y is large enough, the red graph gets above the blue graph, at least if I0 is small enough. All interesting things to think about, all have financial implications. All right, take a breath. Ready? Let's keep going. Now we want to think about immunization. Again, we were just matching present values and durations, but are we immunized? Again, in video 171, we saw that we were not. This function h of I, which is the difference of the present values of the cash flows, the assets minus the liabilities, we would like this to always be greater than or equal to 0, no matter what I is. That would be full immunization. Or at least if I is close to 0.1 from the last video, we'd like to be fully immunized. We'd like to be greater than or equal to 0. That would be Redington immunization. We know from the second derivative test that the key thing to look at is the second derivative of this function at I equals I0. If it's positive, that means the graph is concave up. And since we already know it has a 0 and a critical point at I0, because we'll set the function and the derivative equal to 0, it's going to have a local min at I0 when the second derivative is positive, and that means Redington immunization will be achieved. Or is the second derivative negative, meaning the graph is concave down, and it's like the opposite of Redington immunization? It's definitely not achieved. Is it achieved? The answer is it does depend. Again, we saw when I0 was 0.1 and little y was 3 in the last video that it was not achieved. But can it be achieved? I'm going to go ahead and define this function. So I'm taking those present value formulas and plugging them into Mathematica here. The key thing with this notation here is I is the main variable. By making capital X, capital Y, and little y down here as subscripts, I'm making those sort of parameters, but they are variables as well. This calculation here, plugging in I equals 0.1, little y equals 3, and these values, 75.36, the value of capital X, and 1413.8 or so, the value of capital Y from the last video, into this function, its derivative, and its second derivative gives us the values from the last video, approximately. These first two are essentially 0, okay? H of 0.1 and H prime of 0.1 should be 0. That's just some rounding error. We are essentially getting 0. And the second derivative is negative 1507 or so. And if you look near the end of video 171, I did a second derivative calculation. I didn't actually calculate the negative 1507, I just said it was negative. But if you double check that, you will see it's negative 1507. Okay, that confirms the answers from the last video. We could plot this as we did on a graphing calculator in the last video and see that Redington immunization is not achieved. We get a concave down graph. This value of the second derivative is negative here. We would prefer it to be a concave up graph. Okay? But can we, for example, increase little y to make this graph concave up? And we'll see that we can here. Let's consider a general situation. Okay? I'm defining a new function, capital H, which essentially is the same as little h. But I'm thinking of the variables differently here. I know this is kind of small. Let me make it bigger here. This is kind of confusing. Capital H is going to be a function of little I, and I'm going to graph it as a function of little I and see similar graphs as to what you see above there right now for different values of I0 and little y. But I'm using the little h to define the capital H. Notice I'm plugging in capital X and capital Y, the functions. Capital X of I0, y and capital Y of I0, y in here. Why am I doing that? When I define capital H up here, I had this. Well, here's the key thing, is when I've defined this little h up here, I'm not, that function, as far as Mathematica is concerned, doesn't know whether present values and durations have been matched or not. That's what I did earlier when I found capital X and capital Y was solve. That's what I'm using here when I define those functions. So essentially, by doing this, I am thinking about the specific H functions that solve the problem in the sense of matching present values and matching durations. I'm using the capital X and capital Y functions that I solved for earlier. Okay, but effectively this is the same as little h. I'm calling it capital H just because it's a different thing in Mathematica. It's kind of a complicated looking function. There it is. I guess I could use together to put this in one fraction, but I won't bother. These values should be essentially the same as before, 0, 0, and about, what was it, negative 15 something? Negative 1507, let's see if they are. Yep, this one came out to 0 in Mathematica. This one is so close to 0, it is really essentially 0. And again, about negative 15.07, or negative 1507. I can plot this as a function of I, and this piece of this graph is the same as this graph here, up through I equals 0.25, which is right about here. That's the same thing. I really am graphing little h. This is not a typo here, even though it's a capital H here. And you see the red dot there. But now I can change I0 and little y. If I change I0, I mean the graph does change, but it does stay concave down at the red dot. However, if I increase y enough, the graph can become concave up. And for sure, Redington immunization is achieved, and it looks like probably full immunization is achieved, that this graph is never negative for all values of I. Now, you can't say that for sure because maybe the graph can come back down, but it looks that way at least for, you could say at least for relatively realistic values of little I, which really is down in this range here. Okay, so it looks like if little y is large enough, if that second payment time is large enough, we can achieve Redington immunization. What else can we do here to think about this and confirm this? For a given value of I0, we could ask what value of little y leads to a switch from concave down to concave up at I0 as y increases, in other words, leading to Redington immunization. I could try to do this by hand. I could find that second derivative. I could set it equal to 0 and solve for y, and it's actually not too hard to solve for by hand because look at that formula as a function of y. That's linear. That's really easy to solve for y, actually. I0 is in there in a complicated way, but solving for y is definitely doable by hand. Here's what you get. And then I could make that a function in mathematics. I'd take this expression, type it in here, make this a function of I0. I'm calling it y sol of I0. That's telling me for a given value of the interest rate, I0, that I happen to be thinking about, what value of y, time of the second payment, will lead to the second derivative of the h function being 0, effectively saying as y increases through that value, the graph changes from concave down to concave up. Okay, so we go to a regime of Redington immunization when y is bigger than this solution. When I0 is 0.1, this happens to be about 3.57. Let's see if we can make I equal to about 0.1 here. Close enough. When y is about 3.57, that's where this graph changes from concave down to concave up, right about here or so. It's hard to tell, but that's pretty close. The graph changes from concave down to concave up. That's what this is telling us. A few more graphs we could consider making. We could graph this function as a function of I0. So when I0 is 0.1, for example, we see the solution here is close to 3.57. If the I0 were larger to start with, the solution for this minimal value of y to make the second derivative 0 is lower. This graph is decreasing. And if I0 were smaller, then the value of y sol would be higher. I could graph this over a bigger range. Just seeing if it gets more interesting looking. But those are, here you do have, it seems like a horizontal asymptote, which makes sense from the formula. But as far as realism, it's this kind of range that's more realistic. Okay, it's almost a straight line. There's a little bit of concave down to it, it looks like, but it's almost a straight line. So lots of complicated, but I hope interesting things for you to think about, and think about understanding the big picture more than just solving problems for the exam, but being able to think more generally. I think that will be good for you if you become an actuary or whatever, if you need financial math. Thanks.